Okay, guys, this is the online lecture for Chapter 11, Intraspecific Population Regulation. This chapter deals with the interactions between members of the same species that work to regulate population growth. So as we're talking about interactions between members of the same species, that's where this term intraspecific comes into play. Okay, if we were talking about interactions between members of different species, that would be interspecific. And that's for a later chapter. All right, so we know that no population is able to grow indefinitely. There are always checks and limits on population growth. And the question is, what types of limitations are imposed on population growth by other members of the same species, and how can these interactions regulate the population size? So in Chapter 9, we talked about the exponential population growth model. If you remember, that was dn over dt equals Rn. So basically this is change in population size with change in time equals our intrinsic rate of growth for the population times the population size at any given instant. Okay, now that particular model, that exponential population growth model, is based on certain assumptions about the environment. And these assumptions are, first of all, that resources are unlimited. Okay, that's one. And second, that there is a constant environment. In other words, the environment that the population in question is living in is unchanging. So these are obviously unrealistic assumptions, okay? Resources are always limited. The environment is never constant. It's always in flux, or at least some aspect of it is. And also, as the density of a population increases, demand for resources increases as well. So the question becomes then, what happens to the population when resource consumption is greater than replenishment? Well, the answer is that the resource base shrinks, all right, and mortality increases, and fecundity generally decreases. Or it could be a combination of both of these, all right? Okay, so let's take a look at a figure here that sort of explains all of this. So what you're seeing here are rates of birth and death represented as a linear function of population size. So we have population size here on the x-axis, small to large, and we have our rates of birth and death on the y-axis, low to high. Okay, so the values B sub O, you see here, and D sub O represent the ideal birth and death rates under conditions where the population size is near zero, so very small, and resources are not limiting as a result. Over here on the right, the values of A and C represent the slopes of the lines describing changes in birth rates and death rates as a function of population size. So C here represents the slope of the increase in death rate as population size increases, and A, pointer to work, A represents the slope of the line describing decrease in birth rates as population size increases. Okay, so the population density where births equal deaths and population growth is zero, that is defined as K, what we call carrying capacity. So notice that at this population size, our birth and death rates are the same, right there. So at that particular population size, you would expect the population to be stable. It would not be growing or declining over time, and that's what carrying capacity is. Carrying capacity represents the ability of the environment to support that population sort of indefinitely, okay? All right, for values above N, for values of the population size above K, say over here, for example, births in the blue line are less than deaths, and the population growth rate should be negative because more individuals are dying in any given moment than are being born. For values of population size below K, births are greater than deaths, and there you should have a population growth rate that's positive, all right? Okay, so we can rewrite the exponential population growth model to include variation of birth rate and death rate as population size changes. Doing this changes the pattern of population growth. So as population size increases, birth rate drops and death rate rises. The rate of population growth therefore slows down. So what happens if death rate is greater than birth rate? If death is greater than birth rate, if death rate is greater than birth rate, population growth should be negative and population size declines. And what if death rate is equal to birth rate? Well, if death rate and birth rate are the same, okay, so if deaths equal births, then if we look at our exponential growth model where dn over dt, where we look at the rate of change of population size with time, we see that that should equal 0, okay, when births and deaths are the same. So again, this represents a quantity called K, or carrying capacity for the population, or carrying capacity of the environment for the population. All right, so we can rewrite the equation for population growth to include birth and death rates that vary population size, and we end up with what's called the logistic growth model. So logistic growth model, all right? This model has two components, all right? Well, first of all, let me write down what the actual equation is. So the logistic growth model, again, is dn dt equals intrinsic rate of growth times population size multiplied by 1 minus n divided by k. All right, so that is our logistic growth model, okay? It has two components. It has intrinsic rate of growth multiplied by population size, and 1 minus the population size divided by the carrying capacity, right? There's K, which is our carrying capacity, as we've said. So how does each component then affect population growth? Well, exponential growth is the intrinsic rate of growth times population size. The effect of carrying capacity on population growth is 1 minus the population size divided by K. So when n is much less than K, so when n here is much less than K, the term is close to 0. So think about it. If n is very small, so if n right here is very small and K is large, you divide a small number by a large number, you get a small number. Okay? So 1 minus a small number, 1 minus a small number would give you 1, or a number very close to 1. Now, as n gets larger, you divide n by k, and then subtract that from 1, and you get a number closer to 0. So as n approaches k, the term approaches 0. This term approaches 0, gets smaller as n gets bigger, and that should result in slowing population growth. What if n is larger than k? Well, now you've got 1 minus a number greater than 1. That should give you a negative number, which means negative population growth. So a population grows almost exponentially when small, and the rate of population growth is highest when n equals k divided by 2. So we have our peak rate of population growth when the population size is equal to the carrying capacity divided by 2. This represents what's called an inflection point on our growth curve, right? Inflection point on our growth curve. So let's take a look at that. Okay, so on the left, we see what's called the logistic growth curve. This is a logistic growth curve. So it starts out very high rates of growth. You get an inflection point here, basically, where things begin to change, growth slows, and then eventually flattens out at K, which is carrying capacity. That inflection point right there is K divided by 2. So it's our carrying capacity divided by 2. Again, this is population size on the y-axis, all right? So if we look at this a little bit differently, we can look at the relationship between the rate of population growth and population size. When we do that, the curve takes the form of a parabola, and that's what we see right here. So here we have our population size on the x-axis. Here we have the change in population size with time on the y-axis. So before the inflection point, we have very high rate of growth that begins to slow, and then at the inflection point, it begins to go negative. Population growth goes negative, all right? That's what you see right there. Okay, so if you look at it this way, then again, it shows you that k divided by 2, that is the peak rate of population growth. I shouldn't say it goes negative here. It doesn't go negative. It's still positive, obviously, because it's still increasing. But that's when your rate of growth, rather than accelerating as it's doing over here, begins to decelerate. So it's slowing, still positive, all right? Okay, and then you can see that eventually you reach carrying capacity, and that's the population size that the environment can support. That's the population size at which the population should stabilize at, basically. All right, so let's think about an example. In Chapter 9, we talked about, or had several examples, I think, involving a gray squirrel population when we were talking about life tables and all those calculations. And let's say that we have a gray squirrel population and our carrying capacity equals 200 individual squirrels for whatever environment they're living in, forest patch or whatever. Our intrinsic rate of growth, let's say, is 0.18, and we calculated that from a life table. The initial population size is 30 individuals, okay? So here you have basically the difference between logistic and exponential growth curves for that particular scenario, all right? So you can see that exponential would predict the population would grow indefinitely. And again, this is because, as I said at the beginning of this presentation, exponential growth model assumes that you have unlimited resources and all that. And we said that those assumptions were unrealistic. The logistic model takes into account the fact that resources are never unlimited, they're always limited, and the environment is not stable, it's always changing, okay? And it also takes into account the fact that as the population grows, the resource base per capita per individual declines. So more individuals, the resource base is divided amongst more individuals. Each individual gets less and less, or a smaller piece of that resource pie. All right, so in this gray squirrel population then, where we said that k equals 200 and r equals 0.18, okay, with initial population size of 30, as you see right there, at what size will the population show its maximum rate of growth? Remember, that peak on that curve, the parabolic curve I showed you, or the inflection point on the logistic curve, is k divided by 2. So if k is 200, then it would be, the inflection point would be at 100, right? So that's the answer then. That's the population size at which that population of squirrels would be experiencing its highest rate of growth. From that point on, the rate of growth slows. All right, so the concept of carrying capacity then suggests that there is a negative feedback between an increase in population size and the availability of resources. So as the population density increases, resource availability per capita decreases, as I just said. Eventually, this reduced availability will regulate population growth. So let's introduce an important concept here in ecology, density dependent. So we have density dependent population regulation affects a population in proportion to its size. It's dependent on population density. And there are two ways that population size can be regulated by density. We have, first of all, density dependent mortality. So density dependent death rates. As the population density increases, the rate of mortality increases. And we have density dependent fecundity. So as population density increases, the rate of fecundity decreases. So birth rates should decline as density increases. Both of these can occur simultaneously in a population. All right, so this next figure, notice that for all three of these parts here, A, B, and C, we have population size with K indicated on our x-axis, all right? And then we have the rate of births and deaths indicated on the y-axis. So let's zoom in onto the top one here so you can see it better. Okay, so in A, birth rate is independent of population density, okay? There are situations where that might occur. So our birth rate here is independent of population density. Notice that it stays constant over time, over various population sizes, okay? What changes, however, is death rate. Notice that as population size increases, death rate goes up, all right? That is one possibility there. So at K, carrying capacity, equilibrium should be maintained by increasing mortality, all right? Okay, in panel B, mortality is independent, so notice that it's not changing, right? But our birth rate is dependent on population size. It's declining, so we have an inverse relationship here between birth rate and population size, okay? And again, at K, that's when our birth and death rates should be constant, and that's where the population size should stabilize, okay? Now, in C, we have full-on density-dependent regulation where both birth rate and mortality are density-dependent. You see that as population density goes up, our birth rates decline and death rates increase. But again, the intersection of those two, where those two are equal, births equal deaths, that's our carrying capacity, and that's where we have the basically zero rate of population increase because they cancel out completely. All right, so what factors then can lead to density-dependent regulation? Well, we can have reduced resource availability, I can spell. We have changes in patterns of predation that can come into play, and we can have spread of disease and parasites. And spread of disease is certainly timely, isn't it, with coronavirus going on right now? Makes you wonder if human populations have finally reached sort of a critical level. All right. Not all factors that regulate population growth, however, are density dependent. There are factors that affect population growth to the same degree no matter what the population size is, and those are referred to as density independent factors. So let's write that down. Density independent factors. All right. So, environmental events that affect the population regardless of the number of individuals or if the proportion of individuals affected is the same at any density. This is what density-independent factors are. Tend to be sort of like environmental catastrophes like floods, fires, storms. They will typically affect the same proportion of a small population as they do a large population, and that's why they're referred to as density-independent. All right. So, now let's talk about competition. All right, so competition results when resources are limited. Competition happens when individuals use a common resource that is limited. There is not enough for everyone who needs it. If the availability of the resource is sufficient for all the individuals and does not affect survival, growth, or reproduction, then there is no competition, all right? But generally speaking, resources are going to be limited in such a way that they do affect these aspects of organisms, and so you do get competition. Intraspecific competition is competition among individuals of the same species. Again, we see that intraspecific. Members of the same species usually have very similar resource requirements, so intraspecific competition can be quite intense. And there are basically two types of this, all right? Let me erase all this, okay? We have what's called scramble competition, okay? And in scramble competition, as competition becomes more intense, growth and reproduction are reduced equally among all individuals, and that's the key point there, equally among all individuals. The second type is called contest competition. And in contest competition, some individuals claim enough resources for themselves, so they get what they need, while denying others a share of those resources. So these are generally, scramble and contest competition are generally species specific, although some species show different types at different stages in their life cycle. So the question is then, what are the outcomes of these two different types of competition? Well, scramble competition can result in all individuals having insufficient resources for survival and reproduction and can lead to extinction of the population because everyone's doing poorly, basically, with regard to whatever resource we're talking about. Contest competition only negatively affects the unsuccessful individuals, those who don't get enough of the resource. The successful individuals continue to survive and reproduce, all right? Okay, so competing individuals may interact indirectly or directly. So we're kind of shifting gears here now a little bit. And when individuals are competing indirectly, that is a type of competition referred to as exploitation. All right, exploitation. So here, competition is the result of indirect interactions. Individuals in the population use some resource, and that reduces the amount of that resource available for other individuals. So an example, in a forest, a tree takes up water from the soil, and the amount that it takes up is no longer available to other trees. That leaves less water available for other trees. That's an example of exploitation. All right, we also have what's called interference. Okay, interference competition is the result of direct interaction. So individuals in the population use resources and prevent other individuals from accessing those resources. So as an example, a bird actively defends the area around its nest during breeding season, and that prevents other birds from nesting in the same place. That's interference. So an individual is directly getting in the way of some other individual using a resource. All right. So as population density increases, resources become limited. Either some or all individuals reduce their use of resources, depending on whether we're talking about scramble or contest competition. And this generally slows growth and development first and can lead to density-dependent growth. The growth rate is reduced under conditions of resource competition. All right, so this inverse relationship then between density of the population size, and growth rate has been observed in both animal and plant populations. So as an example, here we have the effect of population density on the growth of individuals of a certain species of plant. This is white clover. All right, and so the growth rate and subsequent weight of the white clover plants declines quite obviously with increasing density of individuals planted in the pot. So here they took individuals, planted them in the pots, and they looked to see what happened over time. Here we have number of plants per pot, right? So these pots had very few, these pots had a lot, very high density of individuals planted. And here we have the mean weight per plant at the end of some specified time period. And you can see that certainly we have the heaviest, most massive plants in pots where the density was lowest, and as density increased, the weight of individuals decreased. So we had a negative or an inverse relationship then between density and growth. So there's a crowding effect here where individuals have less and less resources per capita per individual because there are so many individuals that are competing for that resource. All right, Salt marsh spear-leaf plants were, in one example, were grown in pots in growth chambers at different densities corresponding to densities seen in natural populations. And after about a month, measures of photosynthesis were made and plants were weighed and measured. I'm going to show you a graph of this here in just a minute. I'm going to go ahead and flip over to it. The net rate of photosynthesis in this case was 50% lower in the plants at high density. And so what we see here is our net rate of photosynthesis, and we see how that declines as plant density per pot increases. All right. We also see the same sort of effect here as we did with the white clover in terms of net plant weight or mean plant weight. We have a decrease in that as density increases as well. We also have an increase in the leaf area ratio for individual plants, which indicates an increase in the amount of resources or the allocation of products of photosynthesis, I should say, to produce leaves at the expense of the rest of the plant. So here we have average leaf area, so we can see that leaves did actually get smaller as population density increased. But when you look at the leaf area ratio, so this is looking at the ratio of leaf area to plant biomass, what we see is that even though leaves got smaller, the plants were allocating more of their photosynthetic output toward producing larger leaves relative to the mass of the stems and that sort of thing. So this is seen as basically an adaptation, or I'm sorry, I should say a response to crowding, to light availability, right? When you have a lot of crowding in these plant communities, plants become shaded and restricted, their access to sunlight is restricted, and so it probably is adaptive or beneficial for them to allocate more resources toward leaves rather than stems, okay? So again, don't be confused. Our leaves are getting smaller, but the plants are allocating specifically more resources toward leaf production than they are stems, roots, that sort of thing, okay? All right, so high density then increases competition for light. Okay, so intraspecific competition affects growth and development. We've seen some examples of that. Similar patterns of density-dependent growth are seen in ectothermic vertebrates as well. So ectothermic vertebrates are those that cannot regulate their body temperatures. Their body temperature tends to match the ambient environmental temperature for the most part. So there was a study using wood frog tadpoles that examined the effect of density on individual growth rate and the impacts of intraspecific competition on behavior and morphology. And what this study found was that at higher densities, growth rate decreased, and individuals in higher density populations also had increased activity rates, okay? In other words, that was measured by the amount of time spent moving. They had longer bodies. They had shorter tails, I should say, shorter tails, and they developed wider mouths. All right, so these features enable a tadpole to better compete for resources, especially food. And so this is an example of competition-induced phenotypic plasticity. We talked about phenotypic plasticity before. The norm of reaction was one example of that. The range of values that a phenotypic characteristic can take given environmental variables, right? And so here we have an example of competition inducing phenotypic plasticity, okay? All right, so take a look at this figure here. So what you see again on the x-axis is a number of added competitors, all right? So population density basically. And what we see on the very top is growth rate and how that's affected. So as our population density went up, or number of competitors went up, you see growth rate in terms of grams per day declined, okay? All right, second figure, this is activity. You see that as population density goes up, activity rate goes up. Think about it. If there are more crowded conditions, if you have more competitors around you for whatever it is you're competing for, those individuals who are more actively going after it are probably going to get more of it and survive better. And so you got to be more active in more crowded conditions. And that's what that graph is showing. Then here we have relative body length. So here we have, again, population density going up, and relative body length. So individuals that are longer, tadpoles that are longer, are better able to compete in terms of their food source, whether it's algae or whatever they happen to be feeding upon. Okay. All right. So I'm at about the half-hour point here. I think we're going to stop there. Each of these is going to be about a half hour in length because of file size limitation issues I've been having. So I'm going to stop with this one, and we'll pick up at this point with part 2 for Chapter 11 in the next video.